Okay, now that we've done our calibration, we're ready to collect data on the pavement. Before we get into our dielectric sensor validation mode here, first I'm going to explain where we are on the pavement. So as you probably know, when you're out on a construction site, you typically have construction stakes that are staggered anywhere from every 100 feet to every 1,000 feet. For our purposes, we've decided this location here is at stationing 655 plus 00 with the increasing stationing in the forward direction. As you know, this could also be increasing stationing on a project could also be in the opposite direction that you're collecting. For illustrative purposes, we're going to assume we're moving in the increasing stationing direction. So with that being said, we're going to come back to our software here and look at what we actually have to input to tell the software where we are. So the first thing we're going to do is tell the software where we are in the longitudinal direction. So here we are at station 655 and starting distance 0. The starting distance indicates how many feet beyond the current station you are in the increasing stationing direction, and the starting station tells you exactly that. What is your closest station to the position you're at right now? Next, we're going to move to the decreasing distance / station portion. This check mark would be placed here if we were moving in the down station direction. However, since we are moving in the increasing stationing direction, we're going to keep that checkbox unchecked. Now we're going to move to our lane. In this case, we're going to select travel lane because we're simulating a single lane of pavement here with our longitudinal joint on our right. The next thing we'll be doing here is putting our lateral offset in. I'd like to mention a little bit about lateral offset now, and then we'll decide on what lateral offset to put for our sensor validation. So as we mentioned before, we are at station 655 plus 00. That tells us where we are in the longitudinal direction. However, we also need to tell the software where we are in the offset direction. For this to work, we need to have a single reference position where everything is based from the perspective of that. And for us, that means that we're always looking in the up station direction when we're deciding where we are relative to the reference line. If you'll remember, we selected our center line as our reference line in the project settings, in the project name settings. So in that case, we always need to tell the software where our center sensor or our master sensor is in relation to our reference line. And we need to do that from a consistent perspective. So I would advocate when you're putting your offset into your software, you actually physically look in the increasing stationing direction and stand on your reference line. In this case, if you're looking in the increasing stationing direction, in the current version of the software, you put a negative value if you're moving to the left of the reference line and a positive value if you're moving to the right of the reference line. In the next software, it'll be correctly labeled left and right, but for now, again, left is negative, right is positive. This is our increasing stationing direction. We are to the left of our reference line. Our offsets will always be negative when we're testing in this lane. And that would be true whether the paving was going in the down station direction or if the paving was going in the increasing stationing direction. It's a mouthful, but it is important to make sure you're comfortable with this reference system when you're inputting your offset location. So now we're going to go back to the specific condition that we're in right now, which is right now we would like to validate our sensors. So our validation is conducted by doing what we call a swerve test is one option, a transverse line test is another option, and in RDM 2.0 we'll also have the option of testing with a high density polyethylene block. The first thing we'll take you through now is how to do your validation with what's called the swerve test. Again, with RDM 2.0, this test will have its own module, and you will be able to select which of those three options you would like to conduct for your validation. For the current version of the software, we have to do a little bit of tricky naming convention. So what we do here to indicate that it's a swerve is we actually put a lateral offset that is greater in magnitude than anything we would actually measure in the lane. And this tells our software that we're going to post-process with that this was a validation test, this was not a straight line data collection. So in this case, because we are to the left of our reference line when looking up station, we are going to be indicating a negative value, and we're going to be putting negative 35. So by putting it in the 30s for our magnitude of offset, that tells our processing software that this is actually a validation test. This is not a straight line routine collection. Once we have that input, we'll press accept. Next, we have the option of indicating a lot or a sublot. In this case, we're not tracking lots and sublots, so we're going to go right into our file root name. The file root name is a process that always is appended to our file when it's exported into the finished product folder. In this case, we'd like to start our file name with a 3-digit route number, 061, indicating that we're testing on Trunk Highway 61. Next, we're going to follow that with a dash and the current lift number, which is 1. And at this point, we've indicated the root file name where all of our data collection files will start with this information no matter what type of a test we're doing. So at that point, we're going to press accept. So now we have our file root name. We can delete the comment. That space is for indicating anything abnormal about your current test, and we're actually ready to collect data now. Now you'd like to make sure that your sensors are lined up with the starting station that you put into your software. In this case, since our sensors are lined up properly, we can go into our data collection, scroll down until we see collect distance. We're going to press collect distance, and you see that illuminated orange. Now you see collect file has populated our file name, and we're ready to collect data. To properly conduct a swerve data collection, you want to slowly move your cart from left to right. And your leftmost sensor, when you're moving left, should be approximately 2 feet away from the closest joint. Then you slowly move back to the right, conducting these swerves back and forth approximately once every 50 to 100 feet. And once you get to the right side with your right sensor, you begin to move back with your left sensor. And this process continues until you go approximately 250 feet. And this is actually doing two things for us. It's making sure that our sensors measure similar values to each other, and it's also getting us a good random assessment of the mat. Once you've made it to your stopping point, you can lift up gently on the back of your cart to make sure you're no longer collecting data, and then proceed to go back in the direction you came from. By turning the cart around and doing the similar swerve collection on the way back, you're ensuring that the outer two most sensors are collecting along the same 2 to 10 foot offset as each other. And you're also getting a pretty good assessment of your center sensor too, since in this case the center sensor is covering between 4 to 8 foot offset during this pass. At the end of this pass, we're going to be able to check to see if our sensors are in fact measuring properly. And once we get to the end, we're going to scroll down and press stop and save. We've now successfully completed a Swerve validation pass. After stopping and saving our validation Swerve pass, we are now back to our file information page. Because this is a validation of our sensor, we want to go into our playback last button to identify the results of our Swerve data collection. You can see here that there is some variation in our 3 different sensors. However, the purpose of the Swerve collection is to get a sample of the overall population of the asphalt. So we do expect there to be variations along the pavement itself. What we also expect when we're looking at the results here, and we'll go into the statistics to identify this, is that these 3 different sensors should have similar median results. That is to say, because it is a random sample of the overall population, even though the 3 different sensors are measuring different paths, we've collected enough data that we would expect the 3 different medians to be similar. You can see here our left sensor was 3.51, center sensor was 3.49, right sensor was 3.48. Since all 3 sensors are within 0.03, 0.04, we're well within our 0.08 AASHTO spec, and we can be happy with that calibration or validation. One thing I'd also like to point out is that these numbers are quite a bit lower than what you would expect to see on new construction of HMA pavement. This section that we're testing in the Materials and Road Research Lab parking lot is a chip seal that has been in service for months now. This is the reason the dielectric reading is lower than you would expect on a HMA new construction pavement. We're now going to conduct a transverse line test. This is an alternative way to validate your sensors. In this test, we're going to use a string line to create a transverse line that all 3 sensors will follow. So I'm going to place the string line on our reference line, and after making sure the line is taut, we are going to snap it and create our transverse string line. Everything on the file information inputs will be similar to what was input for the Swerve validation test. The only difference with the transverse line test, we will now put a -45 in for our offset. So that is to say, validations with the Swerve test are in the 30s, and validations with the line test are in the 40s. So we've just went in and switched our lateral offset to -45. I've also went into the file name and indicated -115 to indicate that our right sensor, or our sensor number 115, is the one that's going to be first located along the transverse line. Once this is completed, I'm pressing collect data, collect distance, and then once I've scrolled up and I see my collect file name, I'm ready to proceed forward. In this case, I just want to make sure that I keep my rightmost sensor located centered along this transverse line. And once I've made it to the other side of the lane, I'm going to scroll down and press stop and save. I'll now go back and center my center sensor along the line. Once I have the sensor in position, I can now go back to my file name and change that to read 114 to indicate that the test is now going to be conducted with our center sensor. I'm going to press collect data, collect distance, and now I'm going to proceed forward once I've scrolled up to make sure that it's ready to collect. And we're now seeing data come in for our center sensor on the transverse line test. And we'll proceed forward here until we get to the end of our lane and go back down and press stop and save. We're now ready to collect data with our final sensor of the transverse line test. And that would be with sensor 113. One thing when you're maneuvering the cart is it's always easiest when you're trying to move back and forth to slightly lift up on the back of your cart to allow it to move back and forth more freely. So now, once we're in position with our final sensor, we're going to input 113 corresponding to the sensor number that's being used. Press collect data, collect distance, and when you see your file name correctly displayed, you can move forward with your leftmost sensor centered along that transverse line. And you'll proceed forward until you get to the end of the lane again and press stop and save. Once these three passes have been conducted, you're now ready to go into routine collection mode. Once we've finished our final pass for the transverse line test, we can go to playback last to display our sensor 113 results. So by going into playback last, scrolling down, and going into statistics, we can look at sensor 113 and see that the median is 3.31. You're going to want to write down that number, 3.31. Now, to see the other two sensors, we can go back to our main menu. Now go into playback, and we want to make sure we have the correct project group. We do. Project name, we do. And now we've already checked sensor 113. Now let's look at 114. Playback file. Now we'll scroll down, look at our statistics. Sensor 114 is at 3.25, so it's about 0.06 lower than 113. That's within our AASHTO spec. Next, we're going to go back to the main menu here. Go into playback again. We're in the correct project group, project name. Now we'll select sensor 115 is the only remaining sensor from the transverse line test. Playback file, statistics, Sensor 115 is 3.25. So identical to the center sensor, and both are about 0.06 lower than the left sensor. The reason we had to go into the 3 separate files is we wanted to make sure the exact same line is being evaluated, since in this test we are not getting a very statistically significant sample of the overall population. But this is a great test to make sure all sensors are along the same location, and as you might expect, all 3 should have a very similar result along the same stretch of pavement. The last thing I'll mention with this test is that it can be difficult to conduct when you have an unconfined joint on one side or both sides. It limits the overall distance that you can cover with the transverse line test.